Okay, so we're recording now. So today we're going to cover chapter 27, magnetic forces and magnetic fields. There are a couple differences between electric fields and magnetic fields, as we'll see in the lecture today. First thing we're going to do is take a look at magnetic force, which is an empirical result that had to be determined by experiment. You'll see this force expression referred to as the Lorentz force. Okay. And I'm going to start by introducing the full-blown vector form for the Lorentz force on a charged particle moving in a magnetic field. Since I know you guys are mathematically capable here, a lot of you are in vector calculus. Okay. And this is the equation here, but we need to have a picture to go along with it. But what this equation says is that the force on a charged particle is proportional to its charge times its velocity, but that velocity vector that charged particle has is being crossed, in other words, a cross product with a magnetic field. So let's take a look at a picture here. I'll go ahead and color code everything kind of as I've color coded it here. So if I have a charged particle, we'll take a positive charge. If it's a negative charge, then you plug in minus q and you get a vector in the opposite direction. Suppose this charge is moving in this direction, like so. And suppose we have now a magnetic field, which is going into the page or into the board here. Recall that the dots mean, this is out of the page, sorry. The dots mean out of the page and crosses mean into the page. And I'll go ahead and write that on the side here in a second. So this is our magnetic field, and it's coming out of the screen, right? So dots mean out, and then crosses mean in. So in case you don't remember that from maybe last semester, you might have used that notation a little bit at some point discussing torques and things. Maybe at some point you learned the right hand rule, which we're also going to get a lot of practice with again this semester, today actually. Okay, and so we have magnetic field coming out of the page or out of the screen. We have velocity vector pointing to the right. What's the direction of the force on this charged particle going to be? Well, the force on the charged particle we can get using the right hand rule. And so I'd like to invite you guys to go ahead and use the right hand rule along with me. What you want to do is point your fingers, I don't know if you guys can see. Let me go ahead and stop the share for a second so you guys can see. Can you guys see me a little bit bigger now? This is my right hand here. Your video might be flipped or something. You might think this is my left hand, but this is my right hand. What you want to do is you want to point your fingers in the direction of the velocity and then curl your fingers in the direction of the magnetic field, and your thumb will point in the direction of the force. Okay, so I'm going to go ahead and share screen again. So for me, I'm putting my fingers in the direction of the velocity. Okay, so you can kind of maybe see on the video. And then the magnetic field is coming out of the board. So for me, I have to turn my hand over upside down. My fingers are still pointing in the direction of the velocity, but now I can curl my fingers out of the screen away from the screen, and you can see that my thumb is pointing down right now, right? Regardless of whether the video is flipped or not, you can see my thumb pointing down, right? So that's going to be the direction of the force on this charged particle here. Okay. So we can already see kind of some, maybe we call it bizarre behavior here for charged particles in magnetic fields. And we'll get some practice using the right-hand rule shortly. The next thing that you might be interested in is, instead of having a vector expression like this, is just the magnitude of the force. How can we get the magnitude of this force? Well, we start by taking the magnitude of both sides of the equation. And if you remember the magnitude of a cross product, maybe from last semester, again, referencing torque, right? You pick up a sine theta, you get the magnitude of the two vectors times the sine of the angle between those two vectors. Okay. And so again, we can reference this picture that we have over here. If the magnetic field is coming out of the screen towards me, and the velocity is to the right on the screen, then the angle between those two vectors is 90 degrees in this case here. So theta is 90 degrees here between V and B. And so this is a case where the sine of theta is 1, right? And so the magnitude of the force here in this picture would just be Q times V magnitude times B magnitude. But maybe we can draw another picture here. We'll actually do an example in a little bit, where we have maybe a velocity vector like this for some charged particle. And maybe the magnetic field here is in this direction. Okay. And so now they're making an angle. Maybe we'll use blue here for the angle. Making an angle theta with respect to each other, and it's not 90 degrees, right? And so in this case, the sine of theta would be less than 1. And so there wouldn't be as big of a magnetic force on this charged particle. For example, if the velocity was at an angle of 90 degrees with respect to the magnetic field. So another way of looking at it is to say that only the component that is perpendicular, and we can go ahead and move this here, only the component that is perpendicular to the magnetic field counts towards the magnetic force. Okay, any questions up to this point? Or you guys want to give a thumbs up if you're good with this and we can move forward? Okay, maybe some people need some time to copy. That was about, I want to say that was a little bit over half of you. So give me a thumbs up if you're good to move forward. And we're going to do an example next. Okay. So the next set of examples here that we're going to go over, we're just going to call this right-hand rule practice, okay? So right-hand rule. In general, let me just give some general information about the right-hand rule and then maybe talk a little bit more specific about what we're going to need it for in this class. Because we're not just going to use it for magnetic force. We're going to use it to figure out direction of magnetic fields and all kinds of different stuff. But anytime you have an expression involving a cross product, so let's say some vector C is the cross product of two vectors A and B, I can take my right hand and put fingers in the direction of the first vector in the cross product. So you have to identify the direction of the vector that shows up first in the cross product. So in this case, the vector A. So put fingers in this direction. And then what you do is you curl your fingers. What do I mean by curl? I mean just bend your fingers into the direction of the second vector. So curl fingers into this direction. So you have to identify again, you have to identify the direction of A and put your fingers in that direction. Then you have to curl your fingers into the direction of B. So that's like the part where you kind of need to practice a little bit at first, because you might stick your hand in the direction of A, and then you might have to kind of like contort your arm a little bit until you can twist your fingers in the right direction. So that's the little tricky part about using the right hand rule. Okay. And then once you figure out the orientation of your hand and you can curl your fingers in the direction of that second vector, then your thumb will point in the vector C's direction. So direction is the same as your thumb. And crucial part here, it's the direction of your thumb after you curl your fingers in the direction of B. Okay, it's got to be after. So sometimes I've seen students like put their fingers in the direction of a vector and then like, oh, okay, the vector is in this direction. No, because sometimes you might have to rotate your hand like this and then curl your fingers, right? So you got to be careful. You have to use the right hand rule in this way here described on the right side. So let me throw up a bunch of different pictures now. And I'll just come up with these different configurations and you guys can just practice the right hand rule. And we're going to use the right hand rule to figure out the direction of the force on a charged particle. So here's what we're doing. In order to find the direction of the force, we have to recall the Lorentz force law here. F equals Q V cross B. And we can see that the vector V is the first vector in the cross product. That's why when I first showed how to find the direction, I put my fingers in the direction of V, and then I had to kind of rotate my hand and curl my fingers in the direction of B, okay? So V is the first vector, B is the second vector. Fingers in the direction of V, curl them towards B, and your thumb will point in the direction of the force. Okay. And I'm going to now draw some diagrams here to get us some practice here. So we have a positive charge, let's say moving to the right. And we have a magnetic field here pointing upward, like so. Okay, so you can already go ahead and get started on it if you know what to do. Once I'm done throwing a couple of these diagrams up, then I'll make some more comments. I'll try not to make it too hard to use the right hand rule. Okay, and you can use language like, let's go ahead and number these. You can use language like, okay, the force in 1 is to the left, to the right, up, down, into the screen, out of the screen, right? So those are examples of how you can specify the direction. Go ahead and if you are working on these now, you can go ahead and put your answers in the chat so that other students can compare with what you've got for your answer. Let's go ahead and add in some examples using the cross and dot notation. And maybe number 4 will be our last example here. Okay, so that'll be the last one. So remember, just reminder again, you want to take your right hand, it has to be your right hand, put your fingers in the direction of the velocity of the charge. In this case, all of the charges are positive charge because I don't want to trick anyone here. If it's a negative charge, you have to switch the direction at the last minute because negative charge has a minus sign. These are all positive charges, so stick your fingers in the direction of the velocity. So for example, if you're looking at the camera, number 1 for me looks like this. This is to my right. And then the magnetic field is up. So I have to turn my hand like this, okay, so that I can curl my fingers upward. And then I think you guys can see that my thumb is kind of pointing away from my screen. And so my thumb is pointing away from my screen. So that would be a force coming out of the screen there. Okay. So again, if you are working on these and you have come up with some answers for 2, 3, and 4, go ahead and put those answers in the chat. Again, you can use the language in, out, left, right, up, down. Does anybody have any questions? Give me a thumbs up if you're good and you understand and you're working on it. Okay. All right, good. So let me know if there's any questions. I'll give you guys some time. Okay, we have our first answer for number 2. So you can check to see if you get that same answer, or maybe you get a different answer. Okay, there we go. So now we got some people putting some answers in the chat, so you can check your answers against that. Henry, you might want to check your number 2. Okay, it seems like a decent number of you are getting it. I'll give maybe another 30 seconds or so for those of you who are still working. And then I'll go over each of the examples so we can kind of have a good idea. I'll stop the screen share so you guys can see me use my right hand. Okay, let me go ahead and go over each of them now. I'm going to stop the screen share so you guys can see me like big. Can you guys see me now? Just give a thumbs up. Is the image big? Okay. Let me move this. Okay, so for the first one, again, just going over the first one again, this is my right hand here. Can you guys just give me a thumbs up? Does this appear as my right hand for you guys as well? I hope so. Okay, some of you thumbs up.
Yes, we can see it.
Okay, good. So it is my right hand then. That's good. So sometimes the video is mirrored, right? And then that can be a little bit confusing. So for the first example, the velocity is pointing to the right and the magnetic field is up. So I have to turn my hand like this, like I'm like serving like a plate of food or something, and then curl my fingers up. And that tells me that the thumb is coming out of the screen. So the force is coming out of the screen. Okay. For the second one, it's V at an angle like this. Try and make it look like the example there. But the magnetic field is actually this way. So I got to curl my hand like this. And then my thumb is actually going into the screen now, kind of like towards you guys, right? So into the screen. For example 3, remember that the crosses mean into the sheet or into the paper or into the screen. So in this one, the velocity is up, and then curl your fingers in. And now that's to my left. Okay, that's to my left right there for number 3. And then number 4, I have velocity coming like out at me. And then I have to go like this. I have to actually change direction. So velocity is away from the screen. And then my fingers have to curl in this direction. The magnetic field is to my left. So my fingers curl this way. And the force is down. Okay. So let me go ahead and share the screen again. And then I will fill that in, and then we'll move to the next example. So this one here, the force was into. This one here, the force was to the left. Let's go ahead and label these here. Label them on your diagram so you can go back and look at them. And then for this one, it was down. Okay. Does anybody have any questions about those before we move forward? Give me a thumbs up if you're ready to go. Jiho, are you good? Jaime, Juan? Yeah? Okay. All right. Let's go ahead and move forward. So now I'd like to go over an actual example so we can just kind of warm up and work with the formula a little bit, the Lorentz force. So here in this example, we have a velocity which is at an angle to the magnetic field, 30 degrees here. And the motion is in the XZ plane. And the magnetic field is in the Z direction. So just thinking about the right-hand rule right away, it's always like the first thing you want to do the right-hand rule. Since we just got some practice with it, let's do it now. Everybody just get your right hands up. Put your right hand in the direction of the velocity. So you might have to like turn away from your screen a little bit to do this, right? Maybe I should go this way. So for me, the velocity is kind of coming out like this. And then I got to curl my fingers towards the magnetic field, which is just like a 30-degree angle. So for me, it's like this. If you guys can see the camera. And then the force is going to be downward. That's kind of the first thing I would do when I see a problem like this. So the force here is going to be downward in the negative y direction. This is the force. Okay. Now let me give you guys some information. So suppose we have a beam of protons. Protons have a charge E, 1.6 times 10 to the negative 19 coulombs. And those protons are moving with a velocity 3.0 times 10 to the 5th meters per second. Right? And they're moving through a uniform magnetic field, so it's constant everywhere. And it's quite a large magnetic field. It's 2 Tesla. You guys may have read in the book about the Earth's magnetic field. The Earth's magnetic field is quite small, on the order of 10 to the minus 5 Tesla, somewhere around there. So a magnetic field of 2 Teslas is several orders of magnitude larger than the Earth's magnetic field. So this would be like a magnet system that you'd have set up in a physics lab that specializes in using strong magnets. And this magnetic field is directed along the positive z-axis, like in the diagram. The velocity of each proton lies in the xz plane and is directed 30 degrees with respect to the positive z-axis. Find the force on the proton. Okay, find the force on the proton. So go ahead and work on this one. You can work on this one individually, and maybe on the next example, I'll put you guys in the rooms to work with partners. So for this one, we can just work solo. You may want to use either this equation or this equation that we just take the magnitude. And oftentimes you want to do the magnitude equation because you can find the direction with the right-hand rule. So once you've got an answer, go ahead and put your answer in chat so other students can compare what they've got. Those of you who have answered the question already, perhaps you can now think about whether that is a large or a small force, given that the mass of a proton is 1.67 times 10 to the negative 27 kilograms. So think about whether that is a large or a small force, given the mass of the proton. I think there are still some of you who are working on it, so I can give you guys some more time. No rush. Okay, yeah, so it looks like a lot of you are getting it. So yeah, and a lot of you have had some time to think about that, the size of that force, so that's good. Yeah, it is a large force because the mass of the proton is very small, right? So even a 10 to the minus 14 Newton force can be a large force. The way you determine whether a force is big or not is the acceleration, right? It's Newton's second law. So F equals ma. So you do the force divided by the mass. So yeah, what you do, you plug in your 1.6 times 10 to the minus 19 coulombs, and you plug in the velocity, 3 times 10 to the 5th meters per second. Get your magnetic field in there, 2 Tesla. And you get your sine theta in there, sine of 30 degrees. And you crunch the numbers on the calculator. And you end up with this 4.8 times 10 to the minus 14 newtons. Okay, so let's go ahead and now investigate kind of an interesting property of magnetism that makes it different. It's another thing that kind of makes it different than electricity. And that is the fact that magnetic field lines do not have a beginning or an end. Okay, maybe I should draw this a little bit lower. Let's drag it down. Go ahead and use green again for magnetic field lines. So suppose we have a bar magnet with a north and a south pole like we have here. Now, oftentimes when you see a bar magnet and you want to draw the magnetic field lines for the bar magnet, you tend to think of the field lines as coming out of the North Pole and going into the South Pole. And I'll kind of draw that for you guys now. So kind of out of North and into South, kind of like this. And on the bottom side, like this as well. So out of North and into South. But the problem with this point of view, well, it's the wrong point of view, because magnetic field lines have no beginning and no end. And that has to do with something we'll talk about later. There are no such things as magnetic monopoles. There are electric monopoles. A proton is an electric monopole. An electron is an electric monopole. And they have electric field lines which are coming out of or going into. But the magnetic field lines of a bar magnet, or any magnet really, always hook all the way around and come back into the magnet, and also go straight through the magnet like so. Okay, so this is like one of those common misconceptions where we tend to think about, we tend to think incorrectly sometimes about magnetic fields, because when we first kind of are learning, we think of bar magnets a lot, and bar magnets have a north and a south pole, and the field lines are always shown in the diagrams as kind of coming out of the North Pole and then wrapping around and going into the South Pole. But the field lines also go from the South Pole to the North Pole inside of the magnet. Okay. like I've kind of drawn here. I know it's a little bit messy here, but there it is. Now I made a mention about magnetic monopoles. Let me just kind of draw over here exactly what I mean. So we do have electric monopoles. Electric monopoles are simply the proton and the electron. Those are monopoles. It means that they are a single pole that can exist on its own and have its own electric field. Okay, so here's a proton, right? And a proton, we know a proton has an electric field which looks like this, with electric field lines kind of diverging away from the proton. They're divergent field lines, like so. Maybe put a couple more in here. And this doesn't depend on whether there's a negative charge somewhere in the area. Okay? And the same thing is true for negative charge. So if we have a negative charge, then of course the field lines, they still look like this. And of course this picture is not an electric dipole. I mean to draw these two point charges independent of one another. So I'm not trying to draw a dipole here. This is just one charge, and then I'm looking at another charge. Okay. And so the electric fields exist independent. There's no positive and minus in either case here. We can have an isolated positive charge, we can have an isolated negative charge, and they each have their own electric field. Well, if we were to take a magnet, a bar magnet here, and I'm going to kind of clean some space there. Let's go ahead and use this rectangle function. If we were to take a bar magnet like so, with a north and a south pole, and chop it down the middle, try to separate, let's not use green here, let's go ahead and maybe use red here. Chop it down the middle like this and break it into two. Try to separate the North Pole from the South Pole. What ends up happening is you end up with two bar magnets, and each one still has a North and a South Pole. So we still have a North Pole here, and we still have a South Pole here. But what happens is when we chop it down the middle there, what we end up with is a new South and a new North Pole. Okay. New South and a new North Pole. And that has to do with the fact that the source of magnetism is coming from the atoms inside the bar magnet. Namely the electrons flowing in particular directions around their atoms. Okay, and we'll talk more on that later. But if we have a bar magnet here, we've got a lot of, where's my mouse at? There we go. If we have a bar magnet here, we have a lot of atoms in this magnet, probably iron atoms or neodymium or something. And all those electrons are whizzing around their atoms in a particular direction, or most of them are, and that lines up a nice strong magnetic field inside that material. Okay, and so when you cut it in half, well, you still have the atoms on the other side kind of synced up with the flow of their electrons kind of in the same direction. And so when you separate those two, you simply end up with just two copies of what you had before. You just kind of separated them into two. Okay. Talk more on that later. Maybe we'll cover magnetic domains, which is kind of what I was talking about there later in the lecture. Okay, the next thing that I want to take a look at is the idea of circular motion for a charged particle in a magnetic field. Okay, so suppose that we have, and I'm going to maybe use like a large portion of the screen here to show this. So I want to show it accurately. Suppose we have a proton which has a velocity in this direction here. And suppose that we have a magnetic field which is into the screen here. And suppose that magnetic field is everywhere and it's constant, it's uniformly into the screen here. Go ahead and bust out your right hands. Here's my right hand. And do the right hand rule to solve for the direction of the force. So for me, it looks like this. I put my fingers up, the direction of the velocity. Into the screen is that way for me. And so my thumb says that the force is to the left here. Okay, so there it is. Well, if the force on this charged particle is perpendicular to the velocity like this, what's going to end up happening, it's going to accelerate in that direction, perpendicular to the velocity. So it may end up somewhere over here at some point. It's going to veer off course. And now it's going to have a velocity in this direction because of the acceleration that it experiences due to that force. Like this, right? And now we use the right-hand rule again to determine the direction of the force. So now it's not like this, if you guys can see in the camera. It's not like this, but now the velocity has changed directions, right? And so now when I curl my fingers into the board, you can see that that force is now pointing in this direction. Let's try and make it so that it points kind of to the same location here. Okay. And if you just take your right hand and just kind of move it around in a circle, what you see is that your thumb, as you always curl your fingers in towards the magnetic field, your thumb always points towards the center of a circle. Okay. And so the force always points to the center of a circle. So that should be cluing you guys in, right? Should be thinking centripetal force now, circular motion, uniform circular motion. So the force always points to the center of a circle. Okay. And so what we can do is we can write, and actually let me go ahead and subscript these forces with the letter M here. So that's the magnetic force that we're talking about here, is equal to, go ahead and add some vector signs there, is equal to the centripetal force. Who remembers what the centripetal force is equal to? So you maybe have to think back a little bit to last semester. Go ahead and put it in the chat. I'll let you guys give me the answer here. Keep your brains nice and warm. So what is the centripetal force equal to? Okay, so we have some answers. So mv squared over r, right? Good. So mv squared over r. Okay. And so let's go ahead and get a little bit of a better picture here. So if I were to kind of trace out this circle, kind of just do it with the dotted lines here. It looks pretty good, actually. Here's the radius. That's what we mean by the radius. So the radius of the circular motion. And the V here, this V right here, let me try and make it look a little bit more like the V I drew before, is just the magnitude of this velocity right here. right? So it's the tangential velocity, which stays the same. So it's a uniform circular motion means the speed is constant, right? Okay. And so what we can do is we can write the magnetic force as QVB in magnitude here. Let's maybe not put equals because the force there has a vector sign on it. And then I kind of did the same thing here, right? So let's maybe put an arrow since those aren't technically equal, right? mv squared over r is the magnitude of the centripetal force. So QVB for the magnitude of the magnetic force. Notice that the velocity is always perpendicular to the force, and the force is always perpendicular to the magnetic field, right? They're all 90 degrees with respect to one another in this picture. And so we don't need the sine theta. So we won't put the sine theta there. Go ahead and set QVB equal to mv squared over r, like so. Okay, and so maybe this is a good point to maybe ask you guys to solve for the radius of this centripetal motion. Okay, so maybe you guys can do this. So solve for r. The radius of the centripetal motion here, or of the uniform circular motion. So I'll let you guys work on that. I'll give you a minute or two. You can put your answers in the chat again. Already got a couple people on top of it. That's good. David, maybe you want to cancel a v there in the numerator and the denominator. Okay, so I think we're all on top of it, right? So we just solve for r here, move r to the left side, and then divide by QVB. We can cancel a power of v there, like so. And we end up with mv over qb. Okay. And that's going to be a very important equation in a minute. This equation right here is one particular equation that allows you to build what's called a mass spectrometer. And we'll do an example later with that. So for now, this is just the radius of the circular motion. We'll talk about the design of that kind of device a little bit later. But there's one important and kind of interesting thing that's going on here. And that's that, kind of like we spelled out earlier, that the force is always perpendicular to the velocity, because the force, the Lorentz force, is a cross product between the velocity and the magnetic field. Okay. And so I just want to quickly show something kind of interesting. Since the force is always perpendicular, let me scroll down a little bit. Since the force is always perpendicular, it turns out that it can never actually increase the speed of the particle in circular motion here. And so we can actually show that in the following way. If you remember from last semester, the work energy theorem, that the amount of work done on a particle or some object is equal to the change in its kinetic energy, right? So this is called the work energy theorem. So we're tying in this kind of stuff from this semester into the stuff you learned from last semester. So this is the work energy theorem here. And of course, we know that work is a path integral, right? So the work is the integral on some particular path of the force dot product with some vector dr, which represents the displacement along the path that you're going to calculate the work done by the force. Well, what's interesting here is that if we were to plug in the Lorentz force to this expression, so we'll plug in that force for this force here, without doing much work, we can actually show, I won't ruin the surprise, let's see what happens here. So Q V cross B, and then this thing right here is a vector that's going to be dotted into the vector dr, which is the displacement vector. Okay. If we just use the chain rule here to change our integral from an integral with respect to displacement dr to an integral with respect to time. Let me show you what I mean here. What I mean is use the chain rule to divide this thing by dt and then multiply by dt. So what that means kind of in the math language is simply you're reparameterizing your integral with respect to time instead of with respect to space here. But if we do that, I think we all recognize dr dt is the velocity, right? So we have the integral of q v cross b dot product with v dt. And now that's the interesting part right there. V cross b dot product with v. So what is that going to be equal to? We can actually write down what this is equal to. What happens when you cross two vectors? Your third vector is perpendicular to the first two vectors, right? So maybe you can get a picture going over here. So if I have like two vectors like this, I do the cross product of those two vectors, I get a vector like this. Right, it's perpendicular to both of those vectors. This is three-dimensional, by the way. So let me go ahead and draw like coordinate axes here. So x, y, z. You get a third vector that's perpendicular to the first two. So the red vector here is the cross product of those two blue vectors. But now the red vector is at 90 degrees to the one of the blue vectors. So if I then do the dot product, of the red vector, let's give these vectors names here. So maybe A, B, and C. And if I do the vector C is equal to A, keep it color coded here, A cross B, then that implies that the dot product C dotted with A for any dot product The dot product is equal to the magnitude of the two vectors times the cosine of the angle between those two vectors. Okay, but the angle between the vector C and A is 90 degrees. And so the cosine of 90 is 0. So if I do a cross product between two vectors and then I take that answer and I do a dot product with one of those vectors, I always end up with 0. Because by definition of the cross product, I'm going to end up with a vector that's 90 degrees, has an angle of 90 degrees with respect to those other two vectors. So that's exactly what we have here with V cross B. So V cross B is a vector that's perpendicular to V. In other words, it makes 90-degree angle with respect to V. So if I do a dot product with that vector and the vector V, I get 0. So this is an important result that applies for magnetic fields. So what it means is that the work done by a magnetic field is always equal to 0. So magnetic fields cannot do work on charged particles. So magnetic fields I should probably be a little bit more careful here, because as we'll see later in the semester, there is a connection between magnetic and electric fields. And so maybe I should put here static, the word static. What does static mean? That means it doesn't change with time. So static magnetic fields can do no work on charged particles. Once we have time-changing magnetic fields, those cause electric fields. So you could take the viewpoint that time-changing magnetic fields can do work on charged particles, but it's really the electric field that does the work. The time-changing magnetic field creates an electric field, and then it's that electric field that does the work. So maybe if you want to take that viewpoint, that's fine. But if we go based on the definition here from the Lorentz force, it doesn't even matter if it's a time-changing magnetic field. But it is something to be aware of. So a time-changing magnetic field will give rise to an electric field, which will then ultimately potentially do work on a charged particle. Okay, so that's one thing that's really interesting about magnetic fields there. Okay, so let's go ahead and return to this idea of circular motion here for a magnetic field. And we'll get into an example here. But there's actually, we can talk about that after the example. So let's go ahead and talk about that after the example. So here's the example here. And I'll go ahead and write down the information that we need for the example while you guys are copying down the figure here. But basically what we have is a situation where the velocity has a parallel component to the magnetic field. So the velocity is in the direction of the magnetic field, but there's also a perpendicular component. And so what happens is that the particle spirals about the magnetic field. So you can see that in this image here. So we have like a helical motion for the charged particle. Okay. So let me go ahead and get the information here for this problem. So again, we're looking at a situation where we have a proton. We can use the letter E. 1.6 times 10 to the negative 19 coulombs for the charge. mass of the proton is 1.67 times 10 to the negative 27 kilograms. This charged particle is spiraling in a magnetic field which has a magnitude 0.500 Tesla. I see some. Okay. Okay. Just got some private messages from Roy. I don't know if you guys noticed, but Roy was Roy's another faculty here who he's observing the lecture, but he just messaged me that that he left, so he's no longer here with us anymore. So for this diagram here, right, the charged particle spirals around the magnetic field. Now, the interesting thing, like you would think, okay, doing a problem like this seems kind of weird. What's the application? Well, what's interesting about this problem is this is what gives rise to the aurora borealis. So if you're at the poles on Earth and you see they're called like the northern lights, right? But they can occur at both poles. Those like streams of like green and purpley lights in the sky. That's actually charged particles that are being blasted towards Earth from the sun. The sun's solar wind is like blasting a bunch of charged particles at us. And Earth's magnetic field actually causes those particles to spiral in these helical paths like this. And that actually causes them to radiate light. And so that's kind of what the aurora borealis is. But like I said before, though, Earth's magnetic field is much weaker than half a Tesla here, on the order of 10 to the 5th Tesla. So let me get the rest of the information here for this question. So there's the, oh no, we need the components of the velocity as well. So the x component of the velocity, and see the figure there for the coordinate axes. So we have the magnetic field in the x direction. X component of the velocity is 1.5 times 10 to the 5th meters per second. And then the velocity in the y direction is 0, and the velocity in the z direction is 2 times 10 to the 5th. And actually, let me make sure I get the right sig figs in here. So 10 to the 5th meters per second. I believe this was 1.50. We can put 1.50 there. And the magnetic field is in the x direction here. So maybe we should write bx here. By equals bz equals 0. All right, so that's all of the preliminary information for this question. Now, what's the goal here for this question? So the first thing is we're looking at just a situation with a charged particle and a magnetic field. So it's only the force due to the magnetic field that acts on this proton. And we want to find out what that force is. So part A here is what is the force equal to? So I'll just put F sub m for magnetic force. And then included in part A here in the question, let me go ahead and break it down into another part though. So B is what is the acceleration on that charged particle. And then C, I want to find the radius of that helix. Okay, so we can actually draw on the figure here. So we know that the magnetic force is going to be a center directed force, right? So that's the force right there. And then the radius, right, is going to be, something like this here, right? The radius of the circular motion there. And you use that circular, that radius that we found in the previous example, right? And then finally, or not finally, actually, almost finally, find the angular speed. Something we haven't talked about yet, but we know how to calculate angular speed, right? If we have circular motion, angular speed is the velocity divided by the radius. And then the last part here is what's called the pitch of the helix. Oops, not pith, pitch. And basically what this is delta x for one revolution, for one rotation. That's what pitch is. So pitch means delta x for one revolution. How far does this thing move in one spiral of the helix? Okay, that's pitch. Okay, so that's everything that we're looking for here. And I said we would go into the groups for like one of the next examples. So let's go ahead and do that. I'll put you guys in the rooms. Why don't you guys tell me in the chat, do you want to work with maybe 3 people or 2 people? What do you guys want? I can do groups of 2, groups of 3. Maybe some of you have a group of 2 or something like that. Duke votes for 2. Come on, give me your votes, people. 2, 3, 2, 3, 3. Tied up, right? Or no, it's 2. No, 3, 3, 3. Okay. 3s are taking the lead. That's only 5 people, and we have like 6. We have 15 people in here. Come on. Vote for 2 or 3. Okay, it looks like 3 is going to win here. Let's go ahead and do 3. Maybe some of you can have a group of 2. So let's see here. We break out rooms. Here's what I can do. I can assign rooms manually. So who wanted 2? Duke and Juan Diaz wanted 2. I'll put you guys in the same group. And the rest of you, I will put in groups of 3. Okay, there you go. And of course, I'll come around and see you guys' progress here in about a minute. Jiho, you there?
Example,
How are we doing? Are we doing good?
yeah, we're just getting started on part A.
Juan, you're good too?
Yeah.
Questions? Okay. I'll go to the next room.
Okay.
Hello. How are we doing over here?
Good.
Yeah. Andrea, are you okay?
No, I'm trying to figure out how to set it up.
Okay. Want a little help?
Yes, please.
Okay. Let me go ahead and share back to this screen here. Can you see that?
Yes.
So the starting point is to recognize that because of the cross product, Q V cross B, because of the cross product, only the components of V that are perpendicular to B will count towards the force. So the magnitude here is Q V B sine theta, or you can think of it as Q V perpendicular, which is a slightly easier way to think about it in this particular problem. And so if you have B in the x direction, you don't need to worry about the velocity in the x direction. You only worry about the velocity that's perpendicular to that. So in this case,
it would be Z.
Yeah, the Z, exactly.
Okay.
And of course, like right now, of course, the charge is going to spiral, right, in a circle. So that Z component is going to become Z and Y as it kind of goes through the circular motion, right? But the magnitude of the tangential velocity to the circle will be constant because it's a uniform circular motion. So this V perpendicular will always have a magnitude of 2 times 10 to the 5th meters per second. Does that make sense?
Yes, and then we're going to use the B in the x direction because that's perpendicular to that VZ, correct?
B is in B is in the x direction, so you want to use
The XD. Okay.
Yeah, don't use Vx for this part. Vx will be relevant for the last part, and only the last part. Okay. How about you, Andrew? How are you doing?
Good.
Yeah, does this make sense here? Did you need my help, or you're good, or what's up?
Yeah, you explained it well.
Okay, cool. All right, so I'll go to the next group then.
Yes, thank you.
All right. Room 3. Hello, how are we doing over here?
Still working on it.
Does anybody need any help? Hillary, Jaime?
Not really. I'm still just working through it too.
Okay. Do you want me to give like some hints, or you just want to think through it yourselves?
Maybe a hint for the velocity in part A.
Okay, yeah. And then Jaime in the chat said, for theta, are you using 90 degrees? Yeah, let me just show what I showed to the other group here. So what I showed to the other group was, and I'll go ahead and just kind of, I started by writing this down. But this problem is posed in a way where we have like vector components and stuff, so we might as well take advantage of that. So use the magnitude equation instead. So this one here. And what happens when you take the magnitude of a cross product is you get the magnitude of the two vectors times the sine of the angle between them. And you can go about calculating the magnitude of the velocity and calculating the angle theta and then plugging all that in. But the best way to think of it is that only the velocity that is perpendicular to the magnetic field will actually count towards the force. So you combine the terms v and sine theta to make v perpendicular. So v sine theta is v perpendicular. V perpendicular is what we know. Why do we know v perpendicular? Well, we have magnetic field is in the x direction here, and the velocity has a component in the x direction. So if we ignore the x component, then we automatically have the velocity in the perpendicular component right here. Does that make sense? Okay, and then Henry.
Can you explain it one more time?
Yeah, I'll go for one more
About
time.
the
Yeah.
velocity part.
Yeah, so since this thing is going to be spiraling, right? It's going to be like going and going and going and going. There's a component of the velocity that's in the same direction as the magnetic field. So we can ignore that component because only velocity perpendicular to the magnetic field will give rise to a force.
Oh, yeah.
That comes from the cross product, right?
Yeah.
So if I take two vectors in the same direction and I take the cross product, I get 0. So what I did is I take the magnitude of the cross product formula and I get QVB sine theta. But even better than QVB sine theta is QV perpendicular times B. V perpendicular is just the Z component here. X is in the same direction as B. Vx and Bx are in the same direction. So it'll be Vz that gets plugged in for the V perpendicular, and that'll give rise to the force. And of course, you can see all of this happening if you write down the vectors and do the cross product. So if I actually go down here and I write like I hat, J hat, K hat, right? I could actually go through the motions of calculating the cross product if I want to. You know, you have Vx first, right? This is Vx. Then we have Vy is 0. Vz is, what was given. Then we have Bx, By, and Bz. Right, and most of these are 0, right? This is 0, this is 0, this is 0, right? So at that instant in time, when the particle has this velocity here, the only component that's going to be non-zero is the J component. And what you're going to end up with is Vz times Bx, right? Vx is going to end up multiplying a 0. And then Vz is going to multiply Bx. So when all is said and done, you end up with Vz times Bx for the cross product. And then you have to multiply by the charge to get the magnitude of the force. Is that good?
Okay, that makes it easier. Yeah.
You like the cross product method?
Yeah.
Okay. I try to avoid it because not every student is like in Calc 3 or had matrices. I don't know what it is, but I feel like these days they don't teach matrices in high school even.
Yeah, they don't.
So yeah, it kind of sucks because they're so useful for a lot of different things. But anyways, I think I'll go to the next group now, okay?
Okay, sounds good. Thank you.
You're welcome. Group 4. Hello, how are we doing over here?
We are just comparing answers right now.
So how far are we into the problem then?
I was asking what was part D because it's better write down what to find.
You said part D?
Part D, yeah.
Okay. For part D, let me go ahead and share. Well, I can probably just say, so if you want angular speed angular speed is the tangential speed divided by the radius of the circle. So omega equals v divided by r.
Okay, yeah.
Maybe I could just show on a whiteboard here. So v equals omega times r, right? We could rearrange this so that we have omega equals v over r. Just coming from your rotational motion stuff from last semester, right?
Mhm.
And then this angular speed you could use to calculate a frequency if you want, but we're not asking for it in this problem. We're going to do that next. It's called the cyclotron frequency. Cyclotron is like a kind of particle accelerator. Anyways, John and Jiho, how are you guys doing?
I'm on part C.
On part C? Any questions for me?
I don't know. I'm just doing it right now.
Okay, and then John?
Yeah, I'm also on part C.
Okay, so we're all good then?
I think we're good, yeah.
All right, I'll head to the next room.
Yeah.
Hello, Phoebe, Sean, how are we doing over here? Hello?
So I think we're trying to figure out how to find like part A, and it's kind of confusing because like I know you have to use that equation, the F equals QV times B,
Mm-hmm.
and then like, but the problem is we don't know which V to use. So like thinking maybe like the perpendicular one.
Yeah. So you have the right idea. So when you're in doubt though, like if you really are kind of like you're not sure which one to use, I would say doing the cross product is the best thing to do because it will always give you the right answer. So you could do the cross product. I don't know if you know how to do a cross product. Not everybody's like taken vector calculus or seen this in like pre-calculus. So do you know how to do a cross product or?
I do.
Okay.
It's like Vx on the top, the V is on the top, and then
Yeah.
like I think like F is on the bottom or something.
Exactly.
Yeah.
So you do something like this, right? And then it's like Vx, Vy, Vz, Bx, By, Bz. And then you have to take the determinant of this thing. And a lot of these components are zero, right? So let's make the ones zero that are zero. So all these are zero. Kind of forgot how to use whiteboard because I'm using paint now. There we go. Okay, so those ones are zero. And so you can see because this column has the two zeros there, only this column is gonna, only the J component is gonna survive. The other ones are gonna be zero. Because if I draw a line down the I, the X component here, I'd have two zeros here. So my codeterminant would be zero. Does that make sense, what I just said?
Yeah.
Okay. And if I draw a line down K, then I have Vx times 0 minus Bx times 0. So there's two zeros here. So this codeterminant on the bottom left will be 0 again. So the X and Z components of the force will be 0 at this instant in time, right? Because obviously this thing is spiraling, right? So the components are going to change. But at this instant in time that we're interested in, only the J component is going to survive. So you'll end up with minus J hat times the determinant here, Vx times 0 minus Bx times Vz. Minuses will cancel and you'll be left with Bx Vz. Maybe we could put it as Vz Bx. But the force as a vector at that instant in time is going to be magnitude Vz times Bx in the J hat or the Y hat direction. Usually I write Y hats, X hats and stuff, right? So maybe I should have done it this way. But the important point here is getting, oh, sorry, I forgot the Q. The important point is getting the magnitude, right? So now from doing the cross product, we can clearly see what's the correct thing to do, right? The correct thing to do is to do the z component of the velocity times the magnetic field. And if you look at the figure, you can see, based on the information I was given, that we have velocity in the x direction. That velocity does not give rise to a magnetic force because it's in the same direction as b. So I can maybe stop this share and I can share this, and I already wrote some stuff on this for other students, so it's kind of a little bit cluttered. But if we look over here at the diagram, when the positive charge is right here where it's drawn at the beginning of this helix, it's traveling, it looks like, oh, maybe that's a bad figure there. Okay, you see where the green vectors are. So where the vectors are is a good spot to figure this out. So the magnetic field is always in the x direction, right? But if you look at the green velocity vector, you can see it's broken down into an x component, which is pretty small. That's this component right here. I'm going to highlight it in red. That component does not contribute to the magnetic force at all. And then this component here is along the negative z direction. This component here. So this one does contribute to the magnetic force. So that's your VZ right there.
Oh, okay, that makes sense. So now do I just like plug and chug the numbers in after finding the
For
function?
yeah, for A, so yeah, now you're
Yeah.
ready to plug in numbers, yeah. So
And then
QV perpendicular times B, and then we just got it to be VZ times BX, right?
yeah.
So any other questions, or I should probably just come back, huh?
Yeah, well maybe can you help set up for part B?
Yeah, so it's an acceleration, right? And so the acceleration is, well, or rather the force is F equals ma, right? So you can get the acceleration that way.
Would it be v squared over r or something? Like the
No,
centripetal?
because
No.
we're interested in the acceleration, so F equals ma, and that's it.
Oh, okay, that's very easy then.
Yeah, so we don't need to say centripetal force or centripetal acceleration. We could if we wanted to. I mean, instead of doing F equals ma, I could say A equals V squared over R, but the problem with that is I haven't solved for R yet.
Oh, and then that's where that equation's where part C comes into place, right? After you find the acceleration, you could use that A equals v squared over r to find r. No?
No, probably you want to use the one that we derived earlier. So it's the one where it's like MV divided by QB.
Oh yeah, that's right.
Although you're not wrong, like you could do it that way too. You could say V squared over R. That would work.
So in that case, for part C then, for V, we would use that same one. We would use VZ as well.
Say that one more time.
For part C, to put for the value of V, do we use VZ as well?
No, just the perpendicular again. Or sorry, yeah, that is correct. Yeah, VZ is the perpendicular one. Yep.
Okay.
But here's the important thing to remember, though, that maybe you want to think about a little bit, is that the VZ, that's the velocity, that's the Z component of the velocity that's perpendicular to the circular motion. It's tangent to the circle. Yeah, tangent, sorry, not perpendicular, but tangent to the circle. But that component will change as you go around the circle, right? It's going to change directions if you look in the camera here. So you're going around in a circle, so it changes, right?
Yeah.
But the speed that the charged particle goes around the circle will always be 2 times 10 to the 5th meters per second.
Oh, okay.
So the y and z components will change, but if you do vy squared plus vz squared and then take a square root, that will always give you 2 times 10 to the 5th.
Yeah, that's the magnitude. Yeah.
So I would
Okay.
use this one just so that way we get practice with it because it's like a new equation. We want to make sure we get some practice with it. But
Okay.
you're right. You definitely could use the A equals V squared over R formula. For omega, do you know what to do for this one? That's angular speed.
It's been a long time. I don't remember the formula.
Okay, so for angular speed, you use the relation that the tangential velocity or tangential speed is omega times R.
Oh, and then you would use this. You would use V and R to find W. Okay.
Yeah.
And then I don't understand what part E is, like the pitch.
So that's how far you travel in the X direction after one rotation. So if you look at the picture over here, I can maybe highlight, maybe let's use pink. So from this point here to this point here, that's the pitch.
Oh, so like that's the distance between the two, like
Yeah.
between that.
So it's like it spirals. So it goes like this, and then it comes back to the height that it was at before, and that distance right there is the pitch.
Oh, it's basically T equals BX. Okay.
Yeah, exactly.
Yeah. Okay. I think I should be good then.
Okay.
Okay,
And Sean,
Thank you very much.
Yep, you're welcome. And Sean, I think you're fine.
Yeah. I think I'm fine.
Okay. If you're looking for something, if you're looking to do something harder, maybe crack open the book or something. Okay, I'm gonna go check on some other groups. All right, coming back to check up. What's up, guys? How are we doing?
We pretty much got everything.
Yeah. Okay.
Yeah, we found everything.
So maybe you can just take the time to like read the book or something. Just get a little bit ahead. Don't waste too much time, that kind of thing, because I think there's some other groups who need a little bit more help. So I'm gonna go look at them now. How are we doing over here now?
Good.
What is that?
Finished.
So what part are we on?
I think we finished.
Okay,
I'm on D still.
you're on D. Okay. Do you know how to do D?
No, not at all.
Okay, let me help you out a bit. It's actually pretty simple. It's just coming from circular motion, like back in your first semester of physics. So the tangential velocity is equal to the angular, I should say the tangential speed, V, is equal to the angular speed times R.
Oh, okay.
Just like this, and that's it.
Okay.
And in a little bit, what we're going to do, and maybe you could jump ahead a little bit if you want, is we're going to say that, or rather, we're going to say that the frequency is equal to omega over 2 pi. And then this frequency has a special name. It's called the cyclotron frequency. But we're going to do this in class here, so don't worry about this.
Okay.
Any other questions? So V equals omega times R.
And the V that we're using is not the X, correct? We're still using Z?
Yeah.
Okay.
So let's be careful here. So when we write down F equals Q V perpendicular times B, this is the velocity that is perpendicular. So V perpendicular is perpendicular to the magnetic field. So here we would probably say tangential velocity. And the tangential velocity is the same, or sorry, I should say the tangential speed because I'm not writing it as a vector. But the magnitude of V perpendicular is the same as the magnitude of V tangential.
Okay.
But we maybe should be careful because if we say V perpendicular, but we're talking about circular motion, right? Maybe that gives the impression that the velocity is like this, but really the velocity is like this, right? So this is the correct way. This is the wrong way. I don't know if that was confusing for anybody, but just like a clarification, I guess. So V perpendicular is perpendicular to the magnetic field, but it's also the tangential speed of the particle in uniform circular motion. All right, Andrew, did I hear from you yet? Are you good, or?
How do I do E?
Say that again.
E, the
V?
last one, E.
Oh, E.
Yeah.
The pitch. Okay. So I minimized it. Where is it at? There it is. So let me clear this. So this thing goes around like this in a helix. And let's say this point right here and this point right here are separated by a distance delta x. And this is one revolution of the circular motion. So you want to solve for the time that it takes for one revolution, and then do Vx times that time equals delta x. Does that make sense?
Yeah.
So you need to figure this out from the from one revolution. Okay, so I'll go ahead and go to the next room. And David, if you're looking for something to do, just, I think you mentioned you needed more time on one of the pre-lectures, so maybe just work on that for a little bit so you can catch yourself up.
Okay.
Go into the next group now. Hello, how are we doing? How are we doing over here?
I'm trying to work on the angular velocity.
So for the angular speed, it's simply velocity tangential. So you use this relationship here. So V equals omega times R, right? For circular motion. This right here is the tangential velocity, which happens to be the velocity that is perpendicular to the magnetic field. So the magnetic field is like coming out at us, and then this velocity here, that's the perpendicular velocity. It's also the velocity that is tangent to this circle here. So the tangential velocity is equal to the velocity that's perpendicular to the magnetic field. So does that help out? So if you want to solve this, it's V over R. Does that make sense?
Yes.
Okay. And then Hillary, Jaime.
For one revolution, how do you find revolution again?
So one revolution means you've gone around an angle 2 pi, right?
Yeah.
So if you've gone around one revolution, then that's equal to an angular displacement of 2 pi. But if you want to work in terms of the speed rather than the angular speed, then you could maybe say the distance that you travel around the circle is its circumference, and the circumference is 2 pi times the radius, right?
Mm-hmm.
And so how do I relate the circumference to like the speed? Well, the speed would be the circumference divided by 1 period, right?
Yes.
So this is like t for 1 period. Does that help?
Yeah. Okay.
Okay.
Got it. Thank you.
And you're welcome. And then Jaime, where are you at?
The last question.
You're on E. Okay. For E, it's about, you have a helix, right? And you're going to go around, and this point here and this point here are separated by a distance delta x. And there's an x component of the velocity, right? So there's an x component of the velocity. So you just get the time that it takes to go around one revolution and set that time times the x component of the velocity is delta x. That's how you get the pitch. Does that make sense? So this time right here is the time for one period. Of the circular motion. Does it make sense?
Yes.
Yeah, okay. All right, so I'll go to the next group then, if there are no other questions. Anything else? Okay. Next group. 4. How are we doing over here?
Um, I'm having trouble trying to find the pitch for E.
So that's just the x displacement that occurs in one revolution. So you can figure out the pitch simply with the x component of the velocity times the time it takes to go around one revolution. So this is time. So it's basically one period.
Okay.
Of the circular motion. So do you know how to get the period for the circular motion, or?
Period would just be, two pi r over v.
2 pi r, say it again.
R over v.
Over v, yeah, exactly.
And r would be the mv over qb, right?
Right, but you already calculated it, right? So you can probably just plug it in.
Okay, yeah.
Yeah, And then John and Jiho, do you guys have any questions? Where are you guys at?
I'm stuck on R.
Stuck on R. That comes from what we did a little bit ago. So R is mv over qb. And we got that from the fact that the magnetic force is equal to the centripetal force. So QVB equals mv squared over r. And we solved this for r. Remember we did that as like a little exercise?
Yeah.
So when you solve that, you get r equals mv q over b. And you just have to remember the meaning of v here. So v is the velocity that is perpendicular to b. So in the case of what we're given in the problem, that's that speed of 2 times 10 to the 5th meters per second, right? The tangential velocity for the uniform circular motion is the same as the perpendicular velocity for the magnetic field calculation, or sorry, the magnetic force calculation.
Oh,
Does
okay.
that make sense?
Yeah.
So that speed, the VZ component, that component will change, but the speed in the circular motion will not change. So even though the Z component will change, like the Y component will get bigger and the Z component will get smaller, and then it'll be 0 in the Z direction and it'll all be in the Y direction. But the magnitude Vy squared plus Vz squared will always be 2 times 10 to the 5th. Because again, magnetic field cannot do work on that charged particle. It cannot increase or decrease the speed.
Okay.
So always 2 times 10 to the 5th meters per second for all the velocities involving the circular motion. And then in the last part, that's where finally the x component comes into play. Only in the last part, only in part E. Okay, Ji Ho, do you have any questions?
No, you just answered them.
Okay, all right, so I'll be back around. I am back again. How are we doing over here?
It's going okay, but I just need to like I just need to figure out like what t is, and it's 2 pi over omega. So
No, not quite 2 pi r. You're trying to get the time it takes for one period.
yeah, I'm trying to figure out what t is.
So you got to make sure that you pose it. Go ahead, Sean. You can answer.
It'd be 2 pi r over v, but if you use omega, since v is omega r, you can just cancel out the r's.
Yeah, that's true, but I would suggest putting everything in terms of quantities that you already know, right? So
Yeah.
v, the speed in the uniform circular motion. This is just the 2 times 10 to the 5th meters per second. Times 1 period, the time it takes to go around 1 time, would be equal to the circumference of the circle, right?
I thought that'd be the 1.5 since this is in the direction of motion. The vx.
She's asking about the period though, right? So it would be the speed that it takes, the speed that you're going around the circle with times the time for 1 period would give you the circumference. If you're doing part E, then you got to use the x component. So this would be 2 pi r, and then you could solve for the period. 2 pi r divided by v. Does that make sense, Phoebe?
Yeah, and then after that, you would take that t and multiply by vx, and that's your answer.
That's the answer for E, yeah. So then it would
Okay.
be Ex times big T is delta x.
So r equals mv over qb, so the v's cancel. Well, you would use the answer from part C.
You could just use the answer, but I like your thinking of going after an analytical answer first. So if you do 2 pi and then plug in r is mv over qb, and then there's a v, and then you can cancel the v's. That's a good way of thinking about it.
It's also why I was using omega, because omega can be simplified to just qb over m.
Mm-hmm. Yeah, that is a good point, actually. Okay, so I'm gonna close the breakout rooms in about a minute and kind of just go over everything because we're taking 20 minutes or so to go through this problem. So I think it's about time to go.
Yeah. Okay, thank you, Professor.
Mhm.
Professor, I think you're muted.
Hello. So as you guys are kind of regrouping here, go ahead and type in your answers into the chat that you calculated for parts A, B, C, and D. And I will go ahead and clean this up, and then we'll go ahead and go through the solutions quickly because I think everybody is understanding it. I checked with everyone, right? So hopefully me answering your questions was helpful there. So feel free to type your answers in chat while I'm doing this. So I'm going to start going through the questions. Just keep on typing your answers. And if you notice something like your answer is different from other people's, then you can maybe find your mistake by watching what I do here. So for the magnetic force, only the perpendicular component of the velocity will contribute to the force. In that case, it's only Vz. So the answer here for A should be Vz times Bx times the magnitude of the charge. And I will also go ahead and punch my calculations into Wolfram Alpha here. So and what I get for part A here is 1.6 times 10 to the negative 14 newtons. So again, that force on the order of 10 to the minus 14. For part B here, the acceleration, I simply do the force divided by the mass. You could also do V squared over R, but you haven't yet solved for R, right, in part C. So let's do the question as if we don't know what the radius is yet. It would be F over M. So that would be the 1.6 times 10 to the minus 14 divided by the mass of that charge, which is 1.67. It's the mass of a proton. So 1.67 times 10 to the minus 27. And what we get there for that is 9.6 times 10 to the positive 12. For the radius, we use that circular motion radius that we calculated earlier in the lecture, mv over qb, right? And when we crunch the numbers on this, times 0.5. When I crunch the numbers here on the radius, I end up with 4.175 millimeters. So times 10 to the minus 3. For omega, the angular speed, I simply do the velocity or the speed that this particle is going around in that circle with divided by the radius of the circle. And so that would simply be the 2 times 10 to the 5 divided by my answer in the previous part. And what I end up with is 4.79 times 10 to the 7. That would be units of radians per second. And then for the pitch, I do the x component of the velocity times the time that it takes to go around 1 revolution, which is just the period. And the period is equal to the time it takes to go around one revolution, right? So one revolution would be 2 pi r, the circumference, the distance around a circle is the circumference, divided by the speed at which you go around the circle, which is given by the z component here at this instant in time. So 2 pi r divided by that 2 times 10 to the 5th velocity there. And so we get 1.5 times 10 to the 5th times 2 times pi times the radius of 4.175 times 10 to the negative 3. And then that should be divided by Vz, 2 times 10 to the 5th. And I end up with 1.97 centimeters there, times 10 to the minus 2. Okay, are there any questions? Give me a thumbs up if you're good to move forward. Okay, just about everyone. All right, so the next thing that I'd like to talk about is what's called the cyclotron frequency. A cyclotron is a kind of particle accelerator that's used to, where magnetic fields are used to maintain a circular motion for charged particles, and then energy is added to the system in order to increase the radius of the circular motion or decrease the radius of the circular motion, depending on what you're trying to do. And of course, all the physics that we've done today with magnetic fields applies to a cyclotron. So if you happen to work on a particle accelerator in the future, all of the stuff that we've learned today is like the really important stuff for that. And the cyclotron frequency is defined simply as you would expect. Any frequency can be written as omega over 2 pi, right? Where the frequency here is equal to the angular frequency divided by 2 pi. It just so happens that angular frequency is equal to angular speed whenever we have uniform circular motion. That's kind of one of the confusing things about using the symbol omega for two different meanings, right? Angular frequency and angular velocity. But it happens sometimes. The angular frequency for a charged particle in uniform circular motion we get from this expression here. Maybe I'll use another color here. I'll highlight this in red. Okay, it's the velocity divided by the radius. Divided by 2 pi here. And what we can do is we can plug in for R what we know from the uniform circular motion of a charged particle in a magnetic field. So we have V. Let's go ahead and pull the factor of 2 pi out on the side here so things don't get too cluttered. So 1 over 2 pi, and then it's V over R. R is mv over qb. So we can see cancellation of V's here. So we have 1 over 2 pi. Mass in the denominator. charge in the numerator and B in the numerator as well. Okay. So there's an expression. Maybe we could put this expression in another form if we want to. Actually, I can't remember off the top of my head what form the book actually writes the expression, but important thing here is that there are two things maybe that are interesting here. That is the frequency or the angular frequency omega. So you can work with the frequency f, or you could just work with omega. I think it's pretty clear from here that if f is omega over 2 pi, then omega here is qb over m, right? You can work with either of these two quantities. But what's nice about these expressions here is that if you know the frequency with which charged particles like electrons move around in a circle in something like a cyclotron, or if you happen to be accelerating like ionized atoms or something like that, right? The important thing is that you can use these expressions to measure the charge to mass ratio. So the charge to mass ratio was a really important, it was like an important landmark thing in physics, right? So measuring the charge to mass ratio. It was Thomson, J.J. Thomson, I think is his name. No, I can't remember his first name. But Thomson was the guy who first measured the charge to mass ratio. It's the same guy who had that model of the atom where you have, let me go ahead and stop sharing, where you have like a spherical distribution of charge for the proton. So there's like this sphere that has uniform positive charge density. And then inside of that sphere, there are little dots. And those dots are the electrons. And I remember assigning a problem on your guys' homework. I think it was on a part 2, where you take that sphere of charge and you look at the oscillation of an electron inside of that charge density. And as long as that electron is inside of that sphere, which is what the proton is being considered, then you have simple harmonic motion. But as soon as that electron goes outside of the sphere, then you don't have simple harmonic motion anymore, because the electric field falls off as 1 over r squared outside of the sphere. And the electric field inside the sphere is linear with respect to r, right? But that model obviously was destroyed by quantum mechanics. So the more modern model of the atom is that there are no point charges at all, but the electron is kind of smeared out over a region in the outer shells of the atom. But in fact, the electron even spends some time inside of the nucleus, very close to the protons and the neutrons, as a consequence of quantum mechanics. Now, what is the actual experimental setup for these kinds of things? And that's something that we're going to do. And I think I actually have a picture already. Maybe it's over here. Yeah, but I think I'm getting a little bit ahead of myself. So that's the idea behind circular motion. Everything that we covered there is everything you need to know about magnetic force and circular motion of charged particles in magnetic fields and things like that. And so the next thing to do would be to kind of like what I was alluding to, like with this idea of a cyclotron, like a particle accelerator, and using that to kind of probe the atomic nucleus or something like that. So the direction we're headed now is applications, building devices that we can now use to make more discoveries about the nature of like the atom and charges and things. So that's the idea for the rest of the chapter now, is coming up with interesting designs for devices which we can use to measure things. And so we're not quite at this example yet. There's something I want to do first before we jump into this example, and that is remind you guys of some stuff from some previous chapters. Okay, so let me take this here and move it down. So I'm just going to move it down a little bit here, move it to there. And I want to just remind you guys of a couple of things that are going to be useful for that next example we're going to take a look at. Okay. Now, there's a couple things. So this is like review, but it'll be a quick review. So stay with me here. If I take two plates and I connect them to a potential difference, I have kind of like a capacitor setup, right? What happens is you create an electric field in between the two plates. So if this is the positive, this is the negative here, this is the electric field, right? I can use that electric field to accelerate charges. So I can put a charge right here.
Professor, are you sharing screen?
Oh, sorry. No, I'm not. Oops. And I was talking about all kinds of stuff, wasn't I? Okay, so what I was talking about, obviously you guys had no clue, right? I was talking about this figure here that I have already kind of planned for us to go over, right? But we're not quite ready to go there yet. There's a couple parts that we should analyze for this thing individually. So what I'm going to do is kind of review some stuff from just electricity here first. So if I have two plates like this, and I connect them to a potential difference, right, I'm going to have an electric field in between those two plates. And in the middle of those two plates, the electric field will be straight and constant all along that direction. Actually, maybe it will not be exactly constant everywhere along the midpoint there. But it will be approximately constant along the entire middle line there. And so I can put a positive charge here, Q, in that electric field. I'll give you guys some time to just kind of copy this down. So we just simply have two plates connected to a battery here, potential difference delta V. Give me a thumbs up when you're done copying this down. So just two plates, connect them to a voltage source, electric field in the middle, and then put a positive charge on the side of the positive plate. Okay, two plates, connect them to a voltage source, got an electric field in the middle, approximately uniform, approximately constant there, as long as it's in the middle. Put a positive charge there on the side of the positive plate. What do you get? You get a force on that charge, right? You get a force on that charge. I've been using red for force recently, so let's do that again. So we get a force on that charge, and that force is equal to Q times E, right? And we can write that as a vector equation. Q times E is the force. The force and the electric field are in the same direction, so that force does work on that charge. That force does work on that charge as that charge accelerates through the potential difference. And if that charge is displaced an amount delta x by that electric field, I want you guys to write down an expression like this. The work energy theorem, the amount of work done on that charge is equal to its change in kinetic energy. If it starts off with no kinetic energy, then its final velocity, if the initial velocity is 0, then we're going to have 1/2 mv squared, mv final squared for its final kinetic energy, so that's going to be the change. And the work here we can write as the force times the displacement, right? But we can also write the force times the displacement, the work done on a charge, as Q times delta V. So we have an expression here, if we equate both sides, Q times delta V on the left is equal to 1/2 mv squared on the right. Okay. Solve for V. That's lowercase v. Solve for the velocity. Solve that thing for the velocity. Okay. Solve that thing for the velocity. We've got some answers coming in now. Okay, only 3 of you have given the answer, so maybe I'll give you some more time. Let me give you guys like a minute or two, and I'm going to run to the restroom real quick, so I'll be back. I'm back. Okay, I see a bunch more of you are finished there. So let me just go ahead and do it real quick. So if we want to solve this for v, we have to multiply the 2 over. So 2q delta v. We have to divide by m. And then we have to take a square root on both sides. So the velocity there is given as the square root of twice the charge times the potential difference divided by the mass. And we can take advantage of this idea of accelerating a charge there through that electric field in the following way. What we're ultimately going to end up doing is we're going to have these plates with holes in them, and we're going to use that electric field to launch particles through the hole. And so they're going to go through the holes like this. And as these particles go through the hole, they enter into a new setup, so a different setup. So once we accelerate the charge, so we have this mechanism here of using like a capacitor basically to accelerate charges to get them up to a certain speed. And then after that, we launch them through the hole. So we accelerate them up to a certain speed and launch them through like a little pin-sized hole into another part of our device. Okay. And the next part of our device is going to have both electric fields and magnetic fields. Okay. So let's take a look at that now. And that's good enough for our review. So can you guys give me a thumbs up if you're good on that? Okay. All right, so let's go ahead and go to our next example now. So here in this example, you can see over here on the left side of this diagram here, on this side of the diagram, you have what we just kind of went over. Potential difference on two plates, to have an electric field to accelerate charges. Now the part here, this little tube right here, maybe contains some gas that you're going to ionize. In other words, you're going to charge the gas, charge the atoms in the gas or molecules, and maybe knock some electrons off, and then maybe those electrons are what's going to get accelerated through the potential difference, something along those lines, right? You're going to do something like radiate this gas so that it ionizes and then accelerate those free charges through that potential difference. And you can see the red beam right here is like the charges that you're blasting through this device. And so now we can take a look at the next part of the device here, which is this part, okay, the middle part, and that's what we're going to look at now. You can see that we have magnetic field and electric field here in this part. And so you're maybe wondering, how do we handle that kind of situation? Well, we just handle them separately. We handle the electric force and we handle the magnetic force separately. And then, of course, Newton's laws still apply. So we can sum up the forces and solve from there, right? So whatever it is that we're interested in solving. Now, in this particular case, this device is called a velocity selector. Let me try and draw it in this way here. So we have electric field going down like this. And we have magnetic field going into the board here, into the screen. is our electric field, green is our magnetic field. And then of course we have a charged particle, which is actually part of a beam. So many charged particles flying through this configuration here with electric and magnetic fields as so. Now, if this guy comes in with a velocity v, which is perpendicular to the magnetic field, we're going to have a magnetic force, right? Well, this guy's a charged particle in an electric field, so there's going to be an electric force as well. So get your right hands up. Everybody take out your right hands. Put your fingers in the direction of the velocity. Curl them in the direction of the magnetic field. And tell me the direction of the magnetic force. And so the question is, tell me the direction of the magnetic force. You can use the right hand rule to do that. So remember, we're using the right hand rule. We want to stick our fingers in the direction of the velocity and curl them in the direction of the magnetic field. Okay, and now we're starting to see a lot of agreement here. It's kind of interesting when you have some answers and then other people give other answers. So who's correct? Double check what you've done. Use the right hand rule. Make sure you're using your right hand. Crosses mean into the screen, not out of the screen. So the magnetic field is going into the screen. And I think that's enough of you to go ahead and I'll just quickly full screen myself here. So my right hand is pointing, the fingers are pointing in the direction of the velocity, and then into the screen, that's like towards you guys for me. So the force is up. Where is there it is. Okay. So the force due to the magnetic field is actually up on this particle, right? So if the particle is over here, inside the magnetic field going this way, then it has a magnetic force on it in the upward direction. What about the electric force? What's the direction of the electric force? What is the direction of the electric force? Got one answer already. What is the direction of the electric force? A couple people saying down. What is the direction of the electric force? We have to remember Electric force is Q times E, right? If you have a positive charge, the electric force is in the same direction as the electric field. You have to remember that. F equals QE. So that means the electric force is down. Well, look at that. We have opposite forces here. We can make them equal. And if we make them equal, what that means is that these charged particles will go straight through and they will not be deflected in any way. So for no deflection, let's drop the vector sign actually. For no deflection, the magnetic force should be equal to the electric force. Right? So here's what I want you guys to do. Take this expression and I want you to solve for the charge to mass ratio. We have to also recall the formula that we had before. V equals the square root of twice Q delta V over M. But I want the charge to mass ratio in terms of E and B. Okay, so I want the charge to mass ratio in terms of E and B. Is it clear what we're being asked to do here? So I just want you guys to derive a formula for me. It's not so bad. Magnetic force equals electric force. Use the fact that the velocity is given by square root of 2q delta v over m. You can solve for the velocity from this expression too with the forces. Set them equal to each other and then solve for q over m. Okay. I'm going to give you guys 10 minutes to work on this. And let's go ahead and combine that with like a 5-minute break. I know we've been going for like a long time. So let's combine, let's do like 10 minutes, 5 minutes to work on this, and a 5-minute break. Okay, so meet back at 4:17. Oh, sorry, nope. 4:22. Okay, meet back at 4:22. If you have any questions, put them in the chat. I'll get to them as soon as I see them. Okay, let's go ahead and go over it now. Only a couple of you have given answers, so definitely should go over this. The magnetic force magnitude is QVB. The electric force magnitude is QE. Q's cancel, giving us VB is equal to E, which means that we can solve for V as E divided by B. Right? So since E over B is the velocity, then we can go ahead and write this equal to E over B. Square both sides, divide by 2 and divide by delta V. Excuse me, not V. We get that Q over M is equal to E squared divided by 2 divide by delta V. Yeah, so 2 delta V B squared. And so this kind of device here is what we call a velocity selector. Why is it called a velocity selector? Well, if the velocity of the charged particle is not the velocity that you've selected by setting up an electric and magnetic field, then what happens is the electric and magnetic forces don't cancel each other out. So if the velocity of your particles in this beam are not in a ratio E divided by B, then there's going to be deflection. Those charged particles will be deflected downwards or they'll be deflected upwards, right? Depending on whether the magnetic or electric force is bigger. If the particles are moving faster, then of course the magnetic field is going to be larger because the magnetic force is going to be larger because the magnetic force depends on the velocity, right? If they're moving slower, then it's going to be the electric force that's going to be bigger and going to deflect the particles downward. Okay, so that's the idea behind this device. And you can see over here in the third part of the device, we can put a screen or any number of different things on that third piece there to detect whatever it is that we want to detect, basically. So, like if we want to just blast a bunch of charged particles at a screen and see what shows up on the screen, that's fine. Another example is we could design a mass spectrometer. We would put now a magnetic field in that third part, and then those particles would then undergo like a circular motion, but they would only undergo like half a circular motion, and then they would hit a detector, and based on where they land on the detector, we would know what the mass of those particles is. Okay. And so let's go ahead and take this, copy it, bring it down here, and I'll give you guys an example to work on. What is this, like example 5? So in this particular example, you're going to be reproducing Thomson's experiment, which is basically what's shown here in this schematic, the figure here on the right. So you're going to eventually calculate how fast the electrons are moving here. You're going to calculate the magnetic field that you need in order to have zero deflection. And then with that magnetic field, how will the electron beam behave if you increase the accelerating potential above 150 volts. And the idea here is that you could set up this sort of experiment and measure the charge to mass ratio. But we already know the charge to mass ratio for an electron because we know its charge and we know its mass. So anyway, so assume that we have a potential difference that we use to accelerate these electrons of 150 volts. The electric field has, so the voltage here is, let me actually not write delta V, let me write V because that's what's drawn in the figure. In the figure, it's V right here. So V is 150 volts. The electric field over here in the second region, in the middle region, is 6 times 10 to the 6 newtons per coulomb. In part A, we want to know how fast are these electrons moving. In part B, we want to know what magnetic field is going to give 0 deflection. And in part C, we want to know what happens if we increase V. E minus stands for electron, so E minus beam is the electron beam. So if we, oh, whoops, I put combined what and happens, huh? Should be what? If we increase the accelerating potential, so if we increase V, big V. Okay, so there's the setup. Guess you guys can work on this one individually here. If you guys want to, you can put the formulas in the chat, you know, remind ourselves, write the formula down, helps you commit it to memory, type it in the chat. What formula should I use for part A? What formula should I use for part A? Nobody's given any input yet. Maybe I can help out a little bit. If you want to know the velocity, by the way, maybe some other information you need to know, right? These are electrons, so the charge is minus E, 1.6 times 10 to the minus 19 coulombs. The mass of an electron is 9.11 times 10 to the negative 31 kilograms. So I definitely should give you that information, right? What formula am I going to use? I know the charge, I know the mass, I know the electric field, I know the voltage. Yeah, so David, you got it. That's the one. Square root twice the charge times the potential difference. Well, we're just using V in this case, so big V divided by the mass. Let's go ahead and punch it into the calculator. You guys give me your answers as you calculate them. Okay, I have an answer. I don't want to give it away yet though. Couple people, okay. Yeah. Okay, yeah, that's what I got too. 7.26 meters per second. Okay. How about part B, which is the magnetic field so that there's no deflection? Well, we get that from V equals E over B. So B equals E over V. So B equals E over V. So 6, oh, I forgot to put times 10 to the 6 here for the velocity. Okay, so 6 times 10 to the 6 divided by this answer from before, 0.826 or 27 Tesla. Pretty big magnetic field. What happens to the electron beam if we increase V? Well, if we increase V, what's going to happen is our electrons are going to be traveling faster, right? If they're traveling faster, then the magnetic field is going to exert a bigger force on them than the electric field. If we look at the schematic over here, we can use the right-hand rule to find that the magnetic force will be in the upward direction for a positive charge, but for a negative charge, it will be down. So since we're talking about electrons, the beam will be deflected down. Right? Okay, so there's probably another topic we need to talk about before we end the class, and I have a meeting to go to that I'm already late for because my class runs into the meeting time. So we're going to cover that right now, and that is a force due to a current carrying wire. So here we have, or rather a current carrying conductor in general, right? So here we have a segment of a wire, and there's a current flowing in this wire, current I. Maybe this thing has a cross-sectional area A, and it has a length L for this segment here. So the length of the wire is L. And this thing, we can put it in a magnetic field. Maybe we put it in a magnetic field like this. Okay, so that's into the board, and the velocity of the charges is upward if the current is upward. We have all these charges moving up. Okay. Well, the force on any charge moving perpendicular to a magnetic field is going to be QVB, right? And maybe we could put a sine theta in here if we want to, but in this case, if it's perpendicular, it's just going to be 1. Well, Q times V is like current density, right? So if I were to manipulate this equation a little bit, and the way I'm going to manipulate the equation is we're going to work the volume in here. So current density is current divided by area, right? Let's back up a second here. So let's not do that just yet. So current density is current divided by area, but current density is also equal to the density of free charges, free charge carriers, times the drift velocity times the cross-sectional area. Oh, excuse me, I forgot the charge. So density of charge carriers times the charge of those charge carriers times the drift velocity. And then if I want current, actually, I multiply by A. So NQVD times A. Okay. Now, if I want to express the Lorentz force in terms of current, then the first thing I have to realize is that I have some number of charges, N, in the wire, and each one of those charges will experience a force due to the magnetic field. So this right here is the number of charges, free charges. So each charge experiences a force. So all the forces on all of the charges will add up to give the force on the wire. And so big N is equal to little n times the volume. And little n is the density of free charge carriers, again, same as before. All right. And so I can substitute that in. Excuse me. I can substitute that in. So what that implies is that the force has a magnitude of little n times the area times the length of the conductor times the charge times the velocity of those charges times the magnetic field times the sine of the angle between them. So sine of 90 would be 1. And then I can group these terms in the following way. So N Q V times A, and then L B sine theta. Okay, and now this thing in parentheses here is I. So we have I L B sine theta. Okay, we're gonna have to end it there because I have a meeting to go to. But again, just read the book, right? Go through the pre-lecture assignments. If anybody needs an extension on the pre-lecture assignments, I know a lot of you, kind of already a couple of you have asked me. So if you need extra time, let me know, email me. Just keep working on the assignments so you don't fall behind. And then as soon as I get your email, I'll fix it for you. Okay, but that is the net force on a current carrying wire. right, we're going to end it there.